Hello everyone, we have another video here, this one on 2.5, the fundamental theorem of algebra. Sounds scary, theorems, sound scary, and then here's this really important thing. Well, it is really important. It was proven, it was really an important goal for mathematics in the latter part of the 18th century. Anyway, proven separately by Gauss and a Frenchman, D'Alembert. This really is just a key thing for us to know. I think you know it intuitively in a way that the degree of a polynomial will tell us the potential number of solutions. And what the fundamental theorem of algebra says is that if we consider complex solutions, it will tell us exactly the number. So a 7th degree polynomial will have exactly 7 complex solutions. The other part is that complex solutions come in pairs, so you'll never have an isolated single complex root or zero for a polynomial. They'll always come in matched conjugate pairs. So if it was 7th degree, you could have 2, or you could have 4, or you could have 6 complex solutions, but you're guaranteed at least one real solution in any odd polynomial function, odd degree polynomial function. Okay, so you can scan this, but I would say this one single idea is really the thing we'll refer back to. There's not going to be a lot of work that we do in like the rational zero test. You will have done that other years. It's the way before there were calculators. It's an important concept, but it's nothing that we will be spending lots of time with. But it's a way of, if you were sort of left without a calculator or a way of graphing or something, you could narrow down your possible solutions to guess and check, and you could find the rational roots or the rational zeros through that list of fractions you would get. So this is where we would use synthetic division to speed up that process of finding zeros. Here's actually applying the rational zeros test. Here's a little bit about how the solutions in complex form, that a plus bi, where the a is the real and the b is a real number as a coefficient for the imaginary part, how they always come in conjugate pairs. So it might be fair for me to say, hey, if this is a root, find all of the roots. And if the first root were to be a complex number, you'd know to find its matching pair, its matching partner, and then you could FOIL those together to get a quadratic, and you could divide out the polynomial with that quadratic, possibly getting another quadratic, and then using the quadratic formula to find that. I think there might even be an example, finding the zeros of a polynomial function. So here's a 4th degree, exactly what I was talking about. If you're given 1 0, then you know you've got both of those zeros because they come in pairs. And just, I would say, follow through example 6 on your own. I won't talk you through it now. I will show you though, and here's again using synthetic division, how our calculators can speed up this process. Now, if you were to take this and put this into your calculator and then look at the graph, you could then see that the graph will cross in these 3 places. And by knowing your synthetic division, you could divide out and you could reduce each time by a degree what this original polynomial is, until then you wind up in the end having just a quadratic. And you could put that in the quadratic formula, and then here it is, find the 2 complex roots, okay? So they sort of refer to a method here. I'm going to go to our calculator here and show you just like what I'm really talking about. If, whoops, it's a little bit hard to see this. I think that will work. But I just typed in this 4th degree polynomial. A handy little trick a student actually showed me a few years ago is if you graph the line y equals 0, now when you go to the graph, it's actually easier finding the 0. We have the original polynomial in blue. We have the graphed line y equals 0 here. The way I used to find those intercepts was I would go second, I would go calc, and then I would find the 0, and you need to pinch on either side. I guess I might as well do it. I'll show you each way. So here's the left bound where I have to go over, and I would make sure, just if I'm trying to find this 0 right here, I would make sure I'm on the left-hand side of it, and I'm still on the left-hand side. I know because my y value is negative. That means I'm below the red line. So I would hit enter, And then you get this triangle up here, the pinching arrow, and then I just make sure I go to the right of that 0, and that's when the y value will be positive. There's a sign change there from negative to positive. That's an important concept in Calc. I hit enter, so I'm finding the 0 pinched between these two. I hit enter again, and there it is. The 0 is exactly 0.75, so 3/4, 3/4. That would be one of our rational roots. If I do it the smart way, which I'm telling you about, is I go second this, and then I just do intersect because I have now 2 lines, my red and blue line. So I hit number 5, and all I need to do is just make sure I'm in the vicinity of that, and then I just hit enter a bunch of times until it comes up. And there it is. It's negative 0.333. So it's found the intersection of the blue and red. Very handy trick, negative 1/3. I could divide that through with polynomial long division, okay? So that's really the key thing with the fundamental theorem of algebra. Thank you.